Hello students.
Good morning, sir.
Okay, good morning everyone. So I'll start with my lecture. Today I'm starting with chapter 3, Microscopic Theory of Magnetism. In chapter 2, we had studied the magnetic field produced by a magnetic material, magnetization of the magnetic material, how it produces the magnetic field, and so on. In this chapter, we will learn exactly how this magnetization takes place inside the material. See, magnetization of the magnetic material is due to atomic currents. Atomic currents means because of the electrons which are orbiting around the nucleus. And I had mentioned in the previous chapter, there are three different types of the magnetic materials: diamagnetic material, paramagnetic material, and ferromagnetic material. That means a magnetic material get magnetized in three different ways. They behave in three different ways, or they have three different properties. And we'll in this chapter we will study exactly how it takes place, what happens in the atom to produce a diamagnetic property or paramagnetic property or ferromagnetic property. So first we'll study about the properties of the diamagnetic material, that is the phenomena of diamagnetism. So we'll find here what is the origin of this diamagnetism. That means exactly how the material becomes a diamagnetic material. Now here we'll make a passing reference to what is called as a molecular field inside the matter. Now this magnetization of the material is because of electrons which are orbiting around the nucleus, that means in the atom, in the orbit of the atom. So each electron orbiting around the nucleus produces the magnetic moment. Now this magnetic moment, they interact with the other magnetic moment to produce a resultant magnetic moment, and that resultant magnetic moment is called as a magnetization. Now the molecular field means the magnetic field that is effective in its interaction in atomic currents in atom or molecule. So magnetic field that is responsible for giving a resultant magnetic moment, that means a magnetization of the material. So we will write it as this B suffix M, B suffix M, and with a regular formula it is mu naught into Hm. H is intensity, B is a magnetic induction. Now first let us see what is a diamagnetism, or what is a diamagnetic material. The, any material is made up of atoms. In atoms, electrons are circulating around the nucleus. Then in each orbit, all electrons are revolving almost in the same plane. I'm saying almost in the same plane. The electrons in the different orbits, they will orbit in a different plane, but in the same orbit, electrons will orbit in the same plane. Some of them may orbit clockwise, some of them may orbit anti-clockwise. So I'm saying that electrons are orbiting almost in the same plane. The plane is slightly different. Because what will happen if the plane is same, then suppose there are two electrons which are orbiting in the opposite direction, one clockwise, other anti-clockwise, they will collide. So for that to not happen, electrons are orbiting in slightly different plane in the same orbit. Now, because of this motion, because of the orbital motion, it gives rise to what is called as the orbital magnetic moment. And normally we write it like this: mu suffix L, that is a orbital magnetic moment. It is a vector quantity, and the formula for that is E V R divided by 2. Divided by 2. This is a formula. We have not derived it here. You have learned it in your lower class. In the 12th standard, you have studied the magnetic moment due to the orbital motion of the electron around the nucleus. EVR by 2. E is the charge, V is the velocity, R is the radius. Now, in a given orbit, the velocity is same, radius of the orbit is also same. So, the value of the magnetic moment, value of the magnetic moment is same, EVR by 2. So, in given orbit, the value of the magnetic moment of the electrons is same. Now, what may happen is, in the orbit, one electron may be orbit like this in the anticlockwise direction. This is the electron which is orbiting in the anticlockwise direction. In another orbit, it may orbit in the clockwise direction. But here what happened, this we'll take that these two electrons are orbiting in a slightly different plane, same orbit but slightly different plane. So they will not collide. Now, in what is called as diamagnetic material, there are pair of electrons. They are orbiting in the opposite direction. One clockwise, other anti-clockwise. Because of that, one of the electron will have the magnetic moment, orbital magnetic dipole moment in one direction, and other electron will have in the opposite direction. So value will be same. Value of both will be same because the radius is same, velocity is same, charge is same. But because of that, they are moving in the opposite direction. If you use the right hand thumb rule and you find the corresponding current, and if you find the direction, these two electrons which are orbiting in the opposite direction will have the opposite direction but same magnitude. So resultant magnitude of the orbital magnetic moment of this pair of the electron will be 0. And in diamagnetic material, there will be pair of the electrons which will be revolving in opposite direction, and that will result into the zero dipole moment. So the pair of the electrons will have the zero dipole moment. So the atom will have the zero dipole moment. So the magnetic material will have a zero dipole moment. So it will not be magnetized. So magnetization will be 0. So now here what happens is, in such material, there will be pair of electrons. The electrons are paired. So number of electrons may be 2 or 4 or 6 or 8 and so on. So in the first orbit, number of electrons are 2. So they will cancel. In the next orbit, it may be 8. Then what will happen is, this there will be 3 pairs having the magnetic moment in opposite direction. They are orbiting in opposite direction. So magnetic moment will be 0. So total magnetic moment of the material will be 0. So the material is not magnetized. So these materials are called as a diamagnetic material. So in diamagnetic material, atom, the resultant magnetic moment is 0. So material, the resultant magnetic moment is 0. And this phenomena is called as a diamagnetism. Now, if you keep this in the external field, suppose if you keep it in some external field, some external field is there. Then what will happen is, if you keep in external field, a force will act. And if the force is acting on one electron is in one direction, the force acting on the other electron will be opposite direction. So what happens is, since they are moving in the opposite direction, when the force is acting, when you keep it in field, when the force is acting, the force will act on these two electrons, pair of the electron will be in the opposite direction. So because of which, one of the electron will get accelerated other electron will get deaccelerated. So one of the electron, the velocity will increase, other electron velocity will decrease. So because of the change in velocity, now the magnetic moment, they will have the opposite directions, but value will be different. Values will be different. So values will be different. That means they will not cancel. They are in opposite direction, but value of the orbital magnetic moment of the electrons has changed. For the two electrons, the value has changed. So they are not equal. Since they are not equal, that the total resultant magnetic moment will not be zero. Now, if you use direction of the Lorentz force and so on, then you will find that this resultant will lie opposite to that of the external field, opposite to the external field. So resultant magnetization will be opposite. So that we are not finding it here. But if you use the Lorentz direction for the Lorentz force and so on, you will find that the resultant of this, we can easily find it. The resultant of this resultant magnetic moment will be in the direction opposite to that of the external field. So, uh, so what happens is this type of material, if we keep in extramagnetic field, they will get repelled. But magnetization is not much, as you have seen in the previous chapter. The magnetization product is very small, so they will get weakly repelled. Suppose if you keep this material, diamagnetic material, in the external field, then what happens? Inside the field will get reduced. Field will get reduced inside because the magnetization will get reduced. And if you take this material out of the external field, again its magnetization becomes zero. It does not retain the magnetization. So in the external field, it will be magnetized in the direction opposite to that of the external field. But if we take it out of the field, then what will happen is the resultant magnetization becomes zero because the resultant magnetic moment of the pair of the electron become zero. So this is an example of this, as I mentioned in the previous chapter, is the copper. See, copper, when you keep in very strong magnetic field, you will find it is weakly repelled. So repelled because it gets magnetized in the opposite direction. So this is the property of diamagnetism. The material is called as a diamagnetic material. Then we have to find some physical quantities associated with the diamagnetic material. So we have to develop the theory for diamagnetism. So now what we take for granted here is when you keep the diamagnetic material in the external field, then the force will act, but the radius will not change. Radius will not change. Radius will not change. So it will be in equilibrium. So electron is in equilibrium in the atom. We are doing the assumption we are doing. So now we have to prove this assumption first. So what we'll do is, when you keep in external field, we'll find a change in velocity. Change in velocity means we'll find the change in frequency because V equal to R omega. Omega is 2 pi into frequency. We'll find a change in this frequency, and we'll find it by two different methods. In first method, we'll consider that external force, and by second method, we'll not consider that external force. We will find it by some different way, and we'll find the change in frequency when you keep the frequency of the electron when you keep it in the external field, and we'll show that both these expressions are same. Both the formulas are same. When you consider the theory where the force is used and where you consider theory where the force is not used, the expression will be same. So that means assumption is same, that the radius of the when you keep an extra field, radius of the orbit does not change. So that is what we are going to do it, and afterwards you will find out the expression for magnetic susceptibility. Is very important. Magnetic susceptibility is very important quantity. If you know the magnetic susceptibility, you can find out the permeability, the mu equal to 1 plus chi. So you can find out this. And as we have seen in we have mentioned in the chapter 2 that susceptibility is negative. Here also we will show that it is negative. So now what we do here is, see, let us say then when it is orbiting, it is orbiting when no field is applied. See, when no field is applied, it is orbiting. So velocity is v naught. So now it is orbiting around the nucleus. So it will have a centripetal force. Centripetal force is mv square by r. M is the mass of the electron, m suffix e. V naught is the velocity when it is not kept in the external field. So v suffix 0 square divided by r. R is the radius. Then we can put here v equal to r omega. See, v equal to r omega. So v naught equal to r omega naught. And when you simplify, you will get m suffix e, which is the mass of the electron. Omega naught is the angular frequency square into the radius. So this is the centripetal force which is acting when you keep the when you are not keeping the diamagnetic material in the external field. No field is applied. Then you apply the magnetic field. You keep it in the magnetic field. You keep it in the magnetic field. Then because you keep it in magnetic field, each electron will experience the force like this. QVB sine theta. Theta is 90 degrees in here. See, theta is 90 degrees because the force will be perpendicular to the magnetic field. So magnetic field is applied in such a way that the force is perpendicular to the magnetic field. So sine 90. So that is 1. So QVB. And that force which is exerted, external force which is exerted is Q is E. We take a magnitude because the force is a vector quantity. We take the magnitude. We don't take minus E, but we take E. So Q is this E. Then V equal to R omega. V equal to R omega. And that magnetic field, extra magnetic field is B suffix M. So ER omega BM. Then what happens is, because of the external field, the angular frequency has changed. See, velocity has changed. From V naught it has become V. That means from omega naught it become omega when you apply the external field. So now the total force. So the total force will be this because of the circular motion mv omega naught square r, and because of the external force. Now this external force may get exerted in direction or direction opposite, depending upon that the electron is orbiting clockwise or anti-clockwise. So we write plus minus. So plus or minus depending upon whether the electron is orbiting clockwise or anti-clockwise. And because of that, this total force, the centripetal force, resultant centripetal force will be not different. So it will be, earlier it was me omega naught square r. So velocity has increased. So angular frequency will increase to omega. So me omega square r. So this is a total centripetal force. So because of this original centripetal force and the external force, because of magnetic field, now it will attain a higher or lower depending upon which direction, higher or lower angular velocity, and it will have the resultant centripetal force is this one. Then when you simplify, you get like this. Then you take this MER outside. Then this omega square minus omega naught square is omega minus omega naught into omega plus omega naught, and we get like this. So when omega minus omega naught, we find the change in frequency. Then this R will cancel, and then we find expression for this delta omega, the change in frequency, plus or minus E omega Bm divided by Me omega plus omega naught. Now this will plus or minus depend upon in which direction force get exerted, because I mentioned earlier that one of the electron will get speeded up, other electron get deaccelerated. So this is the equation 1. Then we'll first analyze this equation. See, as I mentioned, electron either speeds up or slows down depending upon the direction of the magnetic force relative to electrostatic force. But what happens is, if we apply the direction for the Lorentz force, in both the cases, whether the velocity increases or decreases, the orbital magnetic moment, resultant magnetic moment, will be in the direction opposite to that applied field. That is what I mentioned earlier. Now, even if we apply large force, the change in the frequency is not much. the velocity will not increase much. The velocity will increase to the small extent, even if we apply large force. So this delta omega is small as compared to omega naught. So we make the approximation that omega plus omega naught, say omega will be almost equal to omega naught. So omega plus omega naught equal to 2 omega. But some change is there. The change is small, doesn't matter. But when you add this, it will not make much difference. So we can take it as twice omega, and you get this equation. And here, this omega and this omega cancels. What you get is E by 2 me B suffix m. Bm is the external field which is applied, and this delta omega is change frequency. Sometimes this frequency is called as a Larmor frequency. It is called as a Larmor frequency. We will not make use of this anywhere, but it is called as Larmor's frequency. Then say, so we have found here the change in frequency when external field is applied. Now we will find the change in frequency by taking another concept. So what happens is, first the magnetic material, no field is applied, and afterwards you keep it in the magnetic field. So that means earlier there was no field and now there is a field. So now what happens is, this electron which is orbiting, there is some area here. There is some area of the orbit. There is some area, and area vector will be perpendicular to that loop. So now what happens is, when you apply the field, earlier the field was 0, now there is a field. So earlier flux was 0, now there is a flux, there is a change of flux. So there is a change of flux. So now we will apply the Faraday's law and find out a change in frequency. Earlier we have found it by using that centripetal force. So now we will find a change in frequency by using a different concept, Faraday's law, and we will show that we get the same equation for the change in frequency. So then we will say that because of that, our assumption that the radius of the orbit when you keep in external field does not change is correct. So now here the change in flux, is the area of that orbit, which is pi r square. R is the radius of the orbit, and changes. Actually earlier one is 0, now it is Bm. Actually dBm is Bm itself. Okay, so it is a change in field. So phi equal to Ba. Now actually that cos of theta is 0. You can find out why it is so. A and B are in same direction. So cos 0 is 1. So there is a change in flux. Then this flux is linked by Dn electron loops. Electrons are orbiting, where Dn is the number of revolutions made by electron during the time in which the field changes. So when the field changes from 0, see the field will change. Earlier there was no field, now there is a field. So the change in field is dBm, and it is in fact Bm. Afterwards we will consider that. So during this time, that electrons makes Dn number of revolutions. So now Faraday's law will apply. According to Faraday, EMF will be generated, n d phi by dt. Then d phi is a dBm by dt. Then n is a number of turns. Now, how many times it has turned is Dn. That's the frequency, number of revolutions. Area is pi r square dBm by dt. Now, from this we will calculate the potential energy of the electron. Electron will gain some potential energy. It will gain some potential energy, or it may lose some potential energy also, depending upon which electrons you consider, whether electron which is moving clockwise or anti-clockwise. The formula for the potential energy is charge into the potential difference. Charge here is E, and EMF is, voltage is E. So E, this EMF pi r square dN dBm by dt. Now this potential energy appears as a kinetic energy. Kinetic energy means electron may get accelerated or deaccelerated. Velocity may change. Then the change in kinetic energy is potential energy. So this potential energy is converted into the kinetic energy. And kinetic energy is the final kinetic energy minus initial kinetic energy, half mv square. So half m is the mass of the electron. Then the final velocity is Vr, initial velocity is V0. So half me Vr square minus half mv naught square. So final kinetic energy minus initial kinetic energy, and that is equal to the potential energy. Then we write V equal to R omega. So first one it is that V square equal to R square omega square, and V naught square is equal to R square omega naught square. Then we have written that equation again here, and what we are going to do here is R square get cancelled throughout, and you get this equation. And this I already made. dBm is just final value of Bm, because dBm equal to Bm minus 0. So dBm is equal to Bm because initially field was 0. Then here we find the average value of this, the average value of that dN by dt. So dN by dt, that is a frequency. There is a frequency. So final plus initial by 2. We take average, and frequency is equal to angular frequency divided by 2 pi. We get this, and we substitute here. So what you get here is this equation, and then this omega naught minus omega minus omega delta omega. Then uh, this omega plus omega naught cancels, and this 2 cancel with this 4 S2, and this pi cancels. So what you get is me delta omega e by m bm. So delta omega is e by 2 me bm. Now this equation 4 and same equation we have found. See that equation 2 which we have found, delta omega e by 2 me bm, is using the centripetal force. This expression we have found by using the another concept, the Faraday's law of electromagnetic induction. We get the same formula. That means we have what we have mentioned, that by keeping it in the external field, the radius of the orbit does not change, so it does not contradict. So it is correct. So that statement is correct. So next we will find out the uh, susceptibility of the diamagnetic material. Now, as I already found that diamagnetic material, we have seen by using the Faraday's law. That means diamagnetism is the result of Lenz's law operating in the atomic scale. See, Lenz's law comes in electromagnetic induction. Now, this is on application of magnetic field, electronic current in each atom are modified in such a way that they tend to weaken the effect of this field. It opposes. See, I also mentioned that the magnetization opposite direction. So the Lenz's law says that opposition is there in electromagnetic induction is always because of opposition. So that's why it weakens the effect of the electric field, so that it gets weakly repelled, or the magnetization is the opposite external field. You can see also from the electromagnetic induction by using the Lenz's law. Then when you keep it in external field, a change in magnetic moment takes place. Change in angular velocity takes place, so change in magnetic moment. You will see delta vector m. By formula, the magnetic moment is I into A. The current is, current is charged by period. So charge into frequency. 1 by period is the frequency. So here since we take a vector quantity, so we write here minus sign. We write here minus sign. So charge is E, minus E. And the change in frequency is delta nu. A is the area. Then this we can write that delta nu is delta omega by 2 pi, because omega is 2 pi nu. So delta omega is omega, this is 2 pi delta nu. So delta nu is a delta omega by 2 pi. Then we have shown that by both the methods we have shown, by centripetal force as well as the electromagnetic induction, by using Faraday's law, Lenz's law, delta omega by is equal to E by 2 me into Bm. This formula we have found. Area is pi r square. Area is pi r square. So this delta Bm is vector quantity. And when you simplify this, this pi cancels. You get minus E square by 4 me r square. Then Bm we are writing is as mu naught hm. Bm we write it as mu naught hm. Suppose the substance contains n molecules per unit volume, then we can write a magnetization of diamagnetic material. Magnetization of diamagnetic material. The resultant magnetic moment divided by volume. See now this resultant magnetic moment. So there are n molecules per unit volume. So it is this per unit volume. So it is n, quantity is n, and the magnetic moment, addition, sum of the magnetic moment. So different electrons in the different orbits, they'll have a different radius. So this formula we substitute here, that n is there into take into account the total number of molecules which are there in the unit volume. So n is there, then it is minus, we substitute here e square by 4 e r square mu naught s suffix m, and r here because the different electrons may have been in a different orbit. So we take for each electron that iteration we write r suffix I equal to 1, 2, 3 and so on. So ri s square. Then hm is nothing but equal to h. In this case hm equal to h. And finally we get like this. Then we compare with the formula which I had stated in the previous chapter. Magnetization equal to the susceptibility, magnetism into the magnetic intensity. So if you compare this, say this quantity m is there, here it is m is there, this quantity h is there, and here h is there. That means chi suffix m, that is diamagnetic susceptibility, is minus ne square by 4 me mu naught summation of ri square. Suppose the orbits are inclined with angle theta, then you take a component of that, Ri cos theta. So this is the final expression for the susceptibility. So what we have found here is the susceptibility of the diamagnetic material, and we get here minus sign. That was what mentioned in the previous chapter. Minus sign. And a minus sign also means that the magnetization opposite to external field. So susceptibility is negative. And if you try to calculate it, it will have very small value. Susceptibility has very small value because when you keep it in external field, the magnetization of diamagnetic material is not very large. It is very small. So this is the theory of the diamagnetism. So with this, I stop here and I will continue on day after tomorrow, that is on Friday. So day after tomorrow I'll take the lecture, Friday at the same time. So there you will learn about paramagnetism and ferromagnetism. Thank you very much.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.